Have you ever wondered how a human can survive in the deadly vacuum of space? Today, we'll take apart a NASA spacesuit layer by layer, revealing the remarkable engineering systems that create a safe, breathable world for a single astronaut. What would happen if an astronaut stepped outside the International Space Station without wearing a spacesuit? It sounds like a scene from science fiction, but the answer begins with a simple fact. Space is not simply very cold or very empty. It is an environment fundamentally incompatible with human life. Unlike Earth, where a thick atmosphere continuously supplies oxygen, maintains pressure, filters harmful radiation, and moderates temperature, the region surrounding the ISS offers almost none of those protections. There is effectively no breathable air, and the pressure is so close to a vacuum that the human body cannot function normally. Contrary to popular myths, a person would not instantly freeze or explode, but unconsciousness would likely occur within seconds as oxygen is rapidly depleted from the bloodstream, followed by irreversible injury if normal pressure and oxygen were not restored quickly. The danger comes not from one single threat, but from several acting simultaneously, each capable of overwhelming the body in its own way. The absence of atmospheric pressure is among the most immediate hazards. Human physiology depends on external pressure to keep gases dissolved in bodily fluids and to allow the lungs to exchange oxygen efficiently. In a vacuum, air trapped inside the lungs expands, making it critical to exhale rather than hold one's breath. Body tissues are elastic enough that they do not burst apart, but moisture on the tongue, in the eyes, and inside the airways can begin to boil because water boils at much lower temperatures when pressure drops dramatically. This phenomenon, known as ebullism, illustrates how closely the human body depends on Earth's atmospheric conditions. Even if someone survived the initial loss of pressure, breathing would remain impossible because there is simply no oxygen to inhale. At the same time, temperature presents a challenge that is often misunderstood. Space itself is not defined by a single temperature. Instead, heat transfer occurs mainly through radiation rather than air. In direct sunlight, surfaces exposed to the sun can exceed well above the boiling point of water, while objects in shadow can plunge to temperatures colder than Antarctica has ever experienced. An astronaut orbiting Earth may move repeatedly between intense solar heating and extreme cold during a single mission, depending on orientation and exposure. Managing these enormous temperature differences requires active engineering rather than relying on insulation alone. Beyond temperature lies another invisible danger: radiation. Earth's magnetic field and atmosphere shield us from much of the sun's energetic particles and a significant portion of cosmic radiation arriving from deep space. Outside those protective layers, astronauts receive higher doses of radiation, particularly during long-duration missions or periods of increased solar activity. While short spacewalks are carefully planned to minimize risk, radiation remains one of the major engineering and medical challenges for future missions to the Moon and Mars. Yet, perhaps the least predictable hazard is one that cannot even be seen. Every day, tiny fragments of natural rock and human-made debris race around Earth at speeds exceeding tens of thousands of kilometers per hour. Many are no larger than grains of sand, but at orbital velocity, even microscopic particles carry enormous kinetic energy. A direct impact can puncture equipment, damage spacecraft surfaces, or threaten an astronaut during a spacewalk. Protection, therefore, depends not only on strong materials, but on multiple layers specifically designed to absorb and disperse impact energy. Taken together, these hazards reveal an important truth. A spacesuit is not clothing in the ordinary sense. It is not designed primarily to keep an astronaut warm or comfortable. Instead, it functions as a miniature spacecraft wrapped around a single human being. It creates breathable air where none exists, maintains life-sustaining pressure, regulates body temperature across extreme environments, removes carbon dioxide, supplies communications, shields against radiation and micrometeoroids, and allows its wearer to work safely in one of the most hostile environments known. Every component serves a purpose, and every system depends on the others. To understand why modern spacesuits are among the most sophisticated machines ever built, we first have to understand the deadly environment they were created to overcome. In the chapters ahead, we will take this remarkable engineering achievement apart, layer by layer, and discover how a personal spacecraft keeps a single person alive in the vacuum of space. A spacesuit does not simply surround an astronaut with oxygen. It recreates one of the most fundamental conditions for human life: atmospheric pressure. On Earth, every breath is supported by the weight of the atmosphere pressing gently against our bodies at approximately 14.7 pounds per square inch, or psi, at sea level. We rarely notice this invisible force because it has surrounded us since birth. Yet every cell, every lung, and every blood vessel depends on it. Remove that pressure, and the body immediately begins to struggle. Oxygen can no longer move efficiently into the bloodstream, dissolved gases expand, and fluids exposed to the vacuum begin to boil at normal body temperature. A spacesuit exists primarily to prevent that chain of events. At the heart of the suit is the pressure bladder, an airtight layer that holds pressurized oxygen around the astronaut's body. If this layer were used by itself, however, it would behave much like an inflated balloon, swelling outward and making movement almost impossible. That is why engineers add another critical component called the restraint layer. Wrapped around the pressure bladder, it limits expansion while maintaining the suit's shape, allowing the astronaut to bend joints, grasp tools, and perform complex tasks without the suit inflating uncontrollably. Together, these two layers create a stable personal atmosphere that moves with the astronaut instead of fighting against every motion. One question naturally follows. If Earth's atmosphere is about 14.7 pounds per square inch, why doesn't NASA simply pressurize the suit to the same value? The answer is mobility. A suit operating at full sea level pressure would become extremely stiff because the difference between the inside of the suit and the vacuum outside would be much greater. Even simple movements such as closing a hand or bending an elbow would require enormous effort. Instead, NASA's Extravehicular Mobility Unit operates at approximately 4.3 pounds per square inch, while supplying nearly pure oxygen. Although the total pressure is much lower, the concentration of oxygen is much higher than in Earth's atmosphere, allowing astronauts to receive sufficient oxygen for normal metabolism while keeping the suit flexible enough for spacewalks. This design is an engineering compromise between human physiology and mechanical practicality, rather than an attempt to replicate Earth's atmosphere exactly. The atmosphere inside the International Space Station is very different. The ISS maintains an environment similar to that found at sea level on Earth, with a pressure close to 14.7 pounds per square inch and air containing about 21% oxygen mixed primarily with nitrogen. That nitrogen is harmless inside the station, but it creates a challenge before a spacewalk. If an astronaut were to move directly from the station's higher pressure environment into the lower pressure suit, dissolved nitrogen in the body could form bubbles in the bloodstream and tissues, producing decompression sickness, commonly known as the bends. Divers can experience the same condition when ascending too quickly from deep water. To reduce this risk, astronauts spend hours breathing pure oxygen before an EVA. The oxygen gradually flushes nitrogen from the body, making the transition to the suit's lower pressure environment much safer. This lengthy preparation may appear inconvenient, but it is one of the most important safety procedures before leaving the station. In effect, every spacewalk begins long before the airlock opens, because the astronaut's body itself must be carefully prepared for the miniature atmosphere waiting inside the suit. Behind every astronaut on a spacewalk is the most important part of the suit that most people barely notice: the backpack. NASA calls it the Primary Life Support System, or PLSS, and it turns the suit from a pressurized shell into a working spacecraft for one person. Inside this compact system are the machines that supply oxygen, remove waste gas, control temperature, power electronics, move air, support communication, and warn the astronaut if something begins to go wrong. The oxygen tanks provide the breathable gas needed to keep the astronaut alive, but oxygen alone is not enough. Every breath also produces carbon dioxide, and in a sealed suit, CO2 would quickly build up to dangerous levels. That is why the PLSS includes a carbon dioxide removal system. Traditional spacesuits used lithium hydroxide canisters, which chemically absorbed carbon dioxide from the circulating air. Newer systems may use regenerable materials, but the purpose remains the same: keep the breathing loops safe and stable for hours outside the station. A fan continuously moves air through the helmet and suit, so oxygen does not simply sit still around the astronaut's face. This ventilation also carries away moisture, heat, and exhaled carbon dioxide, sending the air back through the scrubber before returning it to the astronaut. Batteries power the fans, pumps, sensors, lights, radios, and control systems. Communications equipment allows the astronaut to speak with crewmates and mission control, while warning systems monitor pressure, oxygen flow, carbon dioxide levels, power, and temperature. If one of these readings moves outside safe limits, the suit can alert the astronaut before the situation becomes critical. But one of the hardest problems is not breathing. It is heat. During an EVA, an astronaut is not floating calmly like a statue. They are gripping handrails, turning tools, moving heavy equipment, resisting suit stiffness, and working for hours in a pressurized garment. The human body produces heat even at rest, and during hard physical work, it can generate several hundred watts of thermal energy. Inside a sealed suit, that heat has nowhere easy to go. There is no breeze in space, no surrounding air to carry warmth away, and thick insulation that protects against external temperature extremes can also trap body heat inside. To solve this, astronauts wear a liquid cooling and ventilation garment under the suit. It looks almost like long underwear, threaded with thin tubes. Cool water circulates through those tubes around the body, absorbing excess heat from the skin and carrying it back to the PLSS. There, the heat is rejected through the suit's thermal control system, allowing the astronaut's body temperature to remain within a safe range. Without this cooling loop, the astronaut could overheat even while surrounded by the cold darkness of space. This is one of the strange contradictions of a spacesuit. It must protect someone from freezing, but also stop them from becoming dangerously hot. The PLSS manages that balance minute by minute, quietly doing the work of lungs, air conditioning, batteries, radio, and emergency monitor all at once. What looks from the outside like a simple white backpack is actually the life support core of the entire suit. At first glance, a modern spacesuit appears to be one thick white shell, but it is actually a carefully engineered stack of specialized layers, each solving a different problem that space presents. No single material could simultaneously provide comfort, hold pressure, resist punctures, block intense sunlight, survive extreme temperatures, and remain flexible enough for an astronaut to work. Instead, engineers combine multiple layers into a system where each one performs a specific task. Beginning closest to the body is the comfort layer, designed to reduce friction, improve fit, and help distribute pressure evenly while the astronaut moves. Surrounding it is the pressure bladder, an airtight layer that contains the suit's breathable atmosphere. Without this bladder, oxygen would immediately escape into the vacuum of space. Outside the bladder sits the restraint layer, which prevents the pressurized suit from expanding like a balloon and preserves its shape while allowing controlled movement at the joints. Beyond these structural layers come several layers of insulation. Rather than simply trapping heat, they reduce the transfer of thermal energy by radiation, helping protect the astronaut from dramatic swings between intense sunlight and deep shadow. Outside the insulation is the micrometeoroid protection layer, designed to reduce damage from tiny particles traveling at orbital speeds. Even particles smaller than a grain of sand can carry tremendous kinetic energy when moving at several kilometers per second. So these layers are built to absorb and spread the impact rather than allowing a single object to penetrate directly. The final outer fabric is the suit's first line of defense against abrasion, ultraviolet radiation, and the harsh space environment. Several advanced materials contribute to this protection. Kevlar is valued for its exceptional strength and resistance to puncture, making it useful in protective layers. Nomex provides excellent resistance to high temperatures and does not readily ignite, increasing safety around heat sources. Teflon coatings help resist wear, chemical degradation, and contamination while reducing friction between moving components. One of the most recognizable materials is beta cloth, a fiberglass fabric coated with Teflon that forms much of the outer surface of NASA's spacesuits. It resists flames, ultraviolet radiation, and the gradual damage caused by prolonged exposure to space, allowing the suit to survive repeated missions. The protective design extends well beyond the torso. The gloves are among the most difficult components to engineer because astronauts must manipulate tiny tools while pushing against internal suit pressure that constantly tries to straighten their fingers. The helmet provides a sealed environment with excellent visibility, while the gold-coated outer visor reflects a significant portion of harmful ultraviolet and infrared radiation, reducing glare and helping control heat from direct sunlight. Mounted on the helmet are cameras and lights that allow astronauts and mission controllers to document work and maintain visibility in shadowed areas of the station. During many spacewalks, astronauts also wear the SAFER unit, or Simplified Aid for EVA Rescue, a small backpack containing compressed nitrogen thrusters. Normally, astronauts remain attached to the spacecraft with safety tethers, but if a tether were accidentally severed or disconnected, SAFER could provide limited propulsion to help an astronaut carefully maneuver back to the station. It is intended as an emergency backup rather than a routine navigation system, but it adds an important layer of protection in an environment where even a slow drift away from the spacecraft could quickly become life-threatening. Layer by layer, component by component, every part of the spacesuit exists because space constantly presents another challenge waiting to be solved. Modern spacesuits represent decades of engineering, yet they are far from perfect. Every improvement solves one problem while often creating another, making spacesuit design a continuous balancing act between protection, mobility, weight, and reliability. The familiar white suit that appears effortless on television is, in reality, heavy, pressurized, and physically demanding to wear. Although astronauts float in microgravity, they still work against the suit's internal pressure every time they bend an arm, turn a wrench, or close a hand. Even simple tasks require more effort than they would on Earth because the suit naturally resists movement. One of the greatest challenges remains the gloves. They must protect against the vacuum of space while remaining flexible enough to operate tools, connectors, and scientific equipment. Because astronauts constantly push against the pressure inside the gloves, their fingers, hands, and forearms can become sore or fatigued after hours of work. Engineers have spent decades improving joint designs and materials, yet glove comfort continues to be one of the most difficult problems in spacesuit development. Every spacewalk also has a strict time limit. Oxygen supplies, battery capacity, carbon dioxide removal, cooling water, and other life support resources are all finite. Although emergency reserves are built into the system, astronauts must carefully plan every activity within these limits. Mission planners often schedule EVAs to maximize useful work while maintaining comfortable safety margins. Future exploration introduces even greater obstacles. The Moon presents an environment filled with fine, abrasive dust that clings to surfaces through electrostatic forces. During the Apollo missions, lunar dust adhered to suits, entered spacecraft, scratched materials, and posed concerns for both equipment and astronaut health. Unlike ordinary dust on Earth, lunar dust particles are sharp and irregular because they have not been rounded by wind or water. Mars could prove even more demanding. In addition to abrasive dust, astronauts may have to wear spacesuits for much longer periods while walking across uneven terrain under partial gravity. Missions lasting months or even years will require suits that are more durable, easier to maintain, and far more comfortable than those currently used in Earth orbit. To prepare for that future, NASA and its commercial partners have been developing next-generation exploration suits, including the xEMU program that contributed technologies for Artemis exploration and the new Artemis lunar suits designed specifically for operations near the Moon's south pole. These systems aim to provide greater mobility, improved dust resistance, enhanced life support, and a wider range of motion than previous generations. The goal is not simply to survive on the Moon, but to allow astronauts to work efficiently for extended periods while preparing for even more ambitious missions to Mars. Despite all this progress, the fundamental challenge remains unchanged. Space is still an environment where human beings cannot survive unaided. A spacesuit may look like a bulky white suit, but in reality, it is an entire spacecraft designed for just one person. Every layer, every valve, every pump, every sensor, and every line of software exists to recreate the conditions that Earth provides naturally. Without that remarkable system, the vacuum of space would become unsurvivable within seconds. And that is what makes the modern spacesuit one of NASA's greatest engineering achievements, and one of the most extraordinary machines ever built. Thanks for watching. If you enjoyed exploring the incredible engineering behind NASA's spacesuits, don't forget to like this video, subscribe for more fascinating science documentaries, and I'll see you in the next adventure.